Imagine, for a moment, the single greatest limitation of human civilization. It is not land, the earth is vast. It is not energy, the sun strikes us daily with more power than we can consume. It is fresh water. For 10,000 years, agriculture has been a war against the scarcity of sweet water. We drain aquifers, divert rivers, and watch as our soils slowly turn to dust and salt. But standing quietly on the margins of our world, in the tidal flats, the salt marshes, and the estuaries where no wheat or corn could survive for an hour, is a plant that challenges every assumption we have made about farming. It does not tolerate salt, it craves it. It does not merely survive in seawater, it thrives on it. This is Salicornia, known to history as the glasswort, the sea asparagus, or marsh samphire. It was once the industrial backbone of medieval glassmakers and a delicacy of coastal foragers. Today, as our fresh water sources dwindle and our soils salinate, this forgotten succulent offers a radical proposition. What if the future of agriculture isn't about finding more fresh water, but about learning to farm the ocean? This is the story of the plant that drinks the sea. Salicornia is a genus of succulent halophytic, or salt-tolerant, plants belonging to the Amaranthaceae family. While there are many species distributed globally, from Salicornia europaea in the British Isles to Salicornia bigelovii in the Americas, they all share a remarkable set of physiological adaptations that allow them to grow in full-strength seawater. To the untrained eye, it appears alien. It has no leaves, only segmented, fleshy stems that look like miniature cacti or branched coral. In the spring and summer, it is a brilliant, translucent green. By autumn, many varieties turn a deep, fiery red or purple before releasing their seeds. For centuries, this plant was viewed through a purely utilitarian lens. It was a source of soda ash for industry, or a niche pickled vegetable for sailors and coastal dwellers. But modern agricultural science has begun to rediscover Salicornia as a potential supercrop. It produces an edible oil that rivals soybeans in quality. It generates biomass for fuel. It provides protein-rich fodder for livestock. And, perhaps most importantly, it can reclaim land that has been destroyed by salt, turning barren desert coastlines into productive greenbelts. In this deep dive, we will explore how this humble marsh plant powered the glassworks of Venice, why it fell into obscurity with the rise of industrial chemistry, and how its unique biology might just save our food systems in a warming, drying world. The relationship between humanity and Salicornia is ancient, though rarely written about in the chronicles of kings and conquests. Its history is one of chemistry and survival. In Europe and the Middle East, specifically during the medieval and Renaissance periods, Salicornia was not primarily a food, but a catalyst. The plant is rich in sodium carbonate. When dried and burned, it produces an ash that is exceptionally high in alkali soda. This ash was the critical ingredient required to lower the melting point of silica sand, allowing the creation of glass. The name glasswort, common in English folklore, is a direct nod to this industrial heritage. In the 14th and 15th centuries, vast quantities of Salicornia and related salt marsh plants were harvested and burned in immense pits along the coasts of Spain and the Levant. The resulting barilla, or soda ash, was shipped to Venice, fueling the furnaces of Murano, which produced the finest crystal in the world. Without this humble sea plant, the renowned clarity of Venetian glass would likely never have existed. Simultaneously, in coastal communities across northern Europe, Salicornia was a subsistence food. In the United Kingdom, particularly in East Anglia, it was, and still is, known as samphire, though distinct from rock samphire. It was gathered by the poor during the summer months. Rich in vitamins A, B, and C, as well as essential minerals like calcium and iron, it prevented scurvy in populations that had limited access to fresh garden vegetables. Across the Atlantic, indigenous peoples of North America utilized Salicornia similarly. The bacterial fermentation of the stems could be used for preservation, and the seeds, tiny but nutritious, were occasionally ground into flour. It was a plant of the edges, utilized by those who lived where the land met the water, providing vital nutrients in an environment that offered only shellfish and fish. If Salicornia was so vital to industry and diet, why did it vanish from the collective consciousness? The answer lies in the Industrial Revolution, specifically the shift from biological sourcing to chemical synthesis. In the late 18th century, the demand for soda ash for glass, soap, and paper manufacturing outstripped the supply that could be harvested from burning coastal plants. The price of barilla ash skyrocketed. This scarcity drove the French Academy of Sciences to offer a prize for a method to produce soda ash from common salt, sodium chloride. This led to the Leblanc process, and later the more efficient Solvay process in the 1860s. Suddenly, industrialists could create high-purity sodium carbonate chemically on a massive scale without needing to harvest thousands of tons of marsh plants. The trade in Salicornia ash collapsed almost overnight. The glasswort was no longer needed for glass. Simultaneously, the agricultural revolution was standardizing our food systems. We optimized crops that grew in inland plains: wheat, corn, soy, and rice. These crops required flat land, fresh water, and mechanization. Salicornia, which grew in muddy, tidal, difficult-to-access salt marshes, did not fit the model of the combine harvester or the irrigation canal. Furthermore, as coastal populations urbanized, the generational knowledge of foraging faded. The poor man's asparagus was left behind as supermarkets stocked domesticated vegetables that were uniform, shelf-stable, and traveled well. Salicornia became a ghost, persisting only in the wild margins, remembered only by a few foragers and ecologists, while the world turned its back on the sea and focused its thirst on the rivers. It was not until the late 20th century, as freshwater scarcity began to loom, that scientists like Dr. Carl Hodges and others began to look at the halophytes again. What they found in Salicornia, particularly the species Salicornia bigelovii, was nothing short of a biological marvel. The plant's extraordinary property is its mastery of osmosis. In most plants, salt is toxic. It draws water out of the plant cells, causing them to wither and die. Salicornia reverses this. It actively takes up salt ions into its cells, compartmentalizing them into large vacuoles, storage sacs, within the cell, away from the sensitive metabolic machinery. By doing this, it makes its internal salt concentration higher than the surrounding seawater. This creates a gradient where the plant can actually pull fresh water out of the salty ocean water through its roots. It is a living desalination machine. But the true excitement lies in its yield potential. Research conducted in Mexico, Eritrea, and the United States has shown that Salicornia bigelovii seeds contain approximately 30% oil by weight. This is comparable and often exceeds the oil content of soybeans, which are typically 18 to 20%. The oil is high in polyunsaturated fats, specifically linoleic acid, 75%, making it a healthy edible oil similar to safflower oil. Because the oil is so pure and abundant, it is an ideal candidate for biofuels. In fact, pilot projects have successfully refined Salicornia oil into aviation fuel. NASA and Boeing have both investigated this crop because it offers a fuel source that does not compete with freshwater food crops or require deforestation of rainforests.
After the seeds are harvested, the remaining fleshy stems, the straw, are high in protein but also high in salt. However, if the straw is washed or mixed with other feeds, it becomes a valuable fodder for goats, sheep, and cattle. Perhaps most intriguing is Salicornia's root system. It grows deep and dense. Because it thrives in saline soils where decomposition is often slower, and because it covers land that would otherwise be barren desert, it acts as a significant carbon sink, sequestering atmospheric CO2 into the soil at rates that can rival inland forests.
We live on a blue planet. 97% of Earth's water is saline. Yet our entire agricultural system, our survival, hangs on the fragile 3% that is fresh. We are currently draining ancient aquifers in California, India, and the Middle East to grow thirsty crops in deserts. It is a mathematical impossibility to sustain this forever. Salicornia matters now because it offers an escape hatch from this trap. It proves that we do not need to terraform Mars to find new agricultural land. We have millions of hectares of coastal desert right here, in Mexico, North Africa, Australia, and the Middle East, that could be greened without using a single drop of fresh water. By reviving this lost crop, we are not just reclaiming a nutritious vegetable or a historical curiosity. We are unlocking a new form of agriculture, seawater farming. This is a plant that asks for nothing we are running out of and gives us food, fuel, and restored ecosystems in return. It is a reminder that nature often hides its greatest solutions in the places we least expect, in the salt, the mud, and the tide. All we have to do is look.